Hi everyone, I'm Bai Chen Chen from SUNY Buffalo. Today I will present you with our group's most recent work, ThermoWave, a new paradigm of wireless temperature monitoring, and also a thermal imaging technology that can sense through wall. I'd like to begin with a bigger picture. Wireless technologies have generated an enormous amount of convenience and productivity. However, updating the current infrastructure is in urgent need to keep up with new demands. In order to wirelessly sense everywhere and anywhere, wireless sensing technologies must possess the following traits: high cost efficiency, high sense flexibility, and environmental friendly. The question becomes, what is the solution to the new demand? In current practices toward temperature monitoring, we see two major categories based on their sensing paradigm and output. The first is dot-wise temperature sensing that uses thermoelectric sensor to obtain single temperature value, and the second is thermal imaging, which uses photoelectric sensors to obtain thermal distribution in front of the sensor. Unfortunately, both solutions fail to answer the new demand. They're high cost, their devices are non-flexible for deployment, especially the thermal imaging device that fails in almost all common occlusion scenarios. In the end of their life cycle, they become electronic waste due to the heavy metal content in the device composition. To this end, we propose a new sensing paradigm. Using the next generation wireless sensing technology, mmWave sensing, coupled with next generation wireless sensor, inkable sensor. A concrete example is a recent work from my group, Thermo Tag. It incorporates mmWave sensing in addition to inkable sensor to perform mass item counting applications and achieve ultra-low cost, high flexible, and paper-based eco-friendly sensor. Our next question is, what is the capacity of this inkable plus wireless paradigm? Can it do more than just counting text? What about sensing physical properties? Back to our temperature monitoring topic. Using this new paradigm, we were able to achieve exceptional temperature sensing results. Now, I'd like to introduce our recent work, ThermoWave. ThermoWave is capable of reading both dot-wise temperature and thermal image from a mmWave radar, namely the thermal scanner, and an inkable sensor, namely the Thermo Tag. It bases on the cholesterol material's thermal scattering effect, which links material temperature and the frequency of its mmWave scattering. In another word, the response signal's frequency is causally dependent on the temperature of cholesterol material. To show you in simpler form, the relationship between frequency and thermal scattering and temperature is shown in this mathematical equation. Next, we construct a prototype system. The process goes like this. mmWave scanner continuously gathers thermal scattering response from the sensor, and the response signal is then passed to software module ThermoSense, which implements machine learning models that accurately reads both dot-wise temperature and thermal image of multiple tags simultaneously. In addition to that, we were able to achieve ±1 degree Fahrenheit precision for dot-wise temperature reading and ±3 degree Fahrenheit precision for thermal imaging with high robustness. Benefiting from cholesterol material being soft, Thermo Tag can be placed into almost anywhere, including normally hard to deploy locations and perform sensing under non-rigid surfaces. Next, we'd like to show a thermal imaging experiment. As shown in the video, a person's finger is placed on top of the thermal tag, and we were able to read the temperature very accurately. This cannot be done by any IR camera due to the fingerprint not facing directly to the IR sensor. In conclusion, ThermoWave benefited from this new sensing paradigm and has the potential to be the next generation wireless temperature monitoring technology.